How does the SediMeter determine the sediment level? This is the sensor inside the SediMeter. There is an array of optical backscatter detectors. These are near-infrared light-emitting diodes and a phototransistor that measures the reflected light. So each one of these, in turn, sends out the light and measures the reflection. Based on that, let's say the curve looks like this, with the reflectivity here, the signal here. Based on this, it's rather easy to say that the bottom is between these two. But the question is, where between these two? The difference in height between two detectors is 10 millimeters, 1 centimeter. So if we want to know the bottom level with any precision better than 1 centimeter, we have to interpolate between these. Originally, this was done in the software after importing the turbidity data, because these are actually turbidity measurements with optical backscatter detectors. The interpolation is not linear, therefore there is an algorithm that corrects for the non-linearity. But when we put the cleaner on it, the SediMeter itself had to be aware of where the bottom was in order to operate the cleaner. And therefore we had to put the algorithm for detecting the bottom inside the SediMeter itself. This is the setup for measuring the accuracy of the SediMeter. We've here added small amounts of sediment in the order of tens of grams every time. You can see the layered structure actually. In the end we were adding a bit more, 100 grams or so. And using the SediMeter here in the tube to measure in centimeters in real time using this program here how much it registers. And then we plot that, the cumulative addition of sediment compared to the level, to see how linear it is. Because obviously on the centimeter scale we are not going to get any errors, because the sensors are located where the printed circuit board has the pads, and that's manufactured with high precision. So the question is maybe a tiny bit of variation in the exact location of the optical backscatter detectors, but mostly it's the linearity between the detectors that we want to measure here. I wanted to point out one thing. We stopped this last night, and if you look closely on the graph here, walk up closer, you can see here is the bottom level that was going up when we added sediment, and then when we stopped, it all of a sudden dropped back down by approximately 1 to 1.2 millimeters. That's when the water is going out of the sediment. That's the beginning of the consolidation process. And then after that, it slowly fell a little bit more. But then it started rising. And that's the suspended sediment. Because when we stopped this last night, we couldn't see the SediMeter through the tube. And now you can see it. So that's the fine material. There was a small amount of fine material in this that's sedimented. Here we have plotted the accumulation as measured by the SediMeter on this scale in centimeters, and here the number of grams of sediment that we put into the tank. So we get this blue line of blue dots here. The black line is a straight line through it, the best fit. Now the red here is the difference between the blue and the black, 10 times magnified. So it's 1 millimeter scale here on the red dots. And as you can see, it's a cyclical difference. But then here something happens and it starts going down. So as we can see in the tank, the sediments start to compact. And if we take that into account and divide this line like this, before it starts to compact and after it starts to compact, and take the difference, then we get a straight line of red dots here. And they stay basically within 1 millimeter. Even the maximum are within plus minus 1 millimeter, but most of them are plus minus 0.5 millimeters. So this shows that the error of the SediMeter is cyclical, it's not random, and it has a definite maximum size that's less than 1 millimeter. Let me comment also about a report from the US Army Corps of Engineers regarding this instrument and its accuracy. In the report, they erroneously state that this instrument does not live up to its advertised accuracy. That's wrong, because until that report was made, we never claimed any accuracy. What we claimed in the information material was resolution 0.1 millimeter. And as you all know, resolution and accuracy are two completely different things. The new version, this one here, SediMeter SM3, has a resolution of 0.01 millimeter or 10 micrometers. But therefore we instead say detection threshold 0.1 millimeter, because you can detect an addition or subtraction of material with about 0.1 millimeters. So the reason they came to that conclusion was because they measured the wrong way. They moved the instrument 1 millimeter at a time. But what they should have done is, of course, move it 0.1 millimeter at a time to see if they could detect that. So they moved it 1 millimeter at a time, and then they calculated the statistics wrong, because they assumed a normal distribution, which we've seen here it's not. So, you know. This is a test to see if we can detect an addition of 0.1 millimeters. Here we have measured 2.2 grams, which in this tank corresponds to 0.1 millimeters according to our calculations. We have about 7 measurements where the level is 15.753 centimeters or 15.752 in a couple of cases. So we'll put that in and let it sediment to the bottom. The first measurement will not show anything because it hasn't sedimented yet, but then quick forward and we see here it rose by 0.09 millimeters. That is almost the 0.1 millimeters we had predicted. 0.09 millimeters in that measurement, and we let it stay in a little bit longer to get one measurement more, and here we see that it's exactly the same levels, 15.762, so it rose by 0.09 or 0.095 millimeters. You have to distinguish between resolution, precision and accuracy, and the important thing here is the detection threshold. How little or how much sedimentation or erosion or sediment compaction can you detect? And the question of importance is the precision. And as we've shown, it has a lot of precision.